Review 4. Here we have a graph of the net force and the displacement. And this 2 kilogram mass starts from rest, and we want to know its speed when it reaches x equals 4 meters. We've got the mass there. V naught is 0, and we want to know what VF is, and its final position is at x equals 4 meters. So let's see here. How are we going to do this? I'm looking at this graph and I'm seeing newtons on the vertical axis and unit of meters on the horizontal axis. And if we go back to the big picture equations, we see that there's an equation that looks like this. In other words, if you have a force and you essentially multiply by a displacement, you can get the work done. And what is this quantity here? All of this is the area under the graph. So basically, let's find the area under the graph between x equals 0 and x equals 4, which is that area right there. So let's calculate that. That seems to be pretty easy. 1/2, the base is 4, and the height is 200 joules. Similarly, back in that big picture diagram that we did a few videos ago, there was a very important equation. We'll give it a name later on. It's called the work energy theorem, but it says that the net work done is equal to the change in kinetic energy. And there's the net work done. And so the amount the kinetic energy changes, what's kinetic energy? 1/2 times m, the quantity V final squared minus V initial squared. V initial is given as 0, so we don't need to worry about that. The mass is given as 2. So what does that give us? That looks to me like VF is the square root of 200. Square root of 200 is roughly 14. That's how you do that one. This time, we're graphing net force with time. In the last one, we had net force and displacement. So we've got a slight nuance that's different from what we just had. What's the acceleration at a time of 5.5 seconds? All right, so that would be right there. That's the time we're interested in. And how are we going to find that? Well, anytime it asks for acceleration, it's a good idea to remember Newton's second law, which is that the net force is equal to the mass times the acceleration. Do we know the net force at that time? We sure do. We can approximate it. It's going to go up, 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 right about to there, maybe 27 newtons from the graph, roughly. And the mass, we're told from the graph right here, I'm circling it now, is 9 kilograms. That means that the acceleration is going to have a magnitude of 3 meters per second squared. We're just choosing easy numbers here so that we don't have to rely on a calculator. What about the impulse? What's the impulse delivered between those two times? Once again, back to our big picture diagram, the impulse was symbolized capital J, and it is basically force multiplied by time, which for this graph, you can see we've got force on that axis, we've got time on that axis. So once again, we are looking for area here between 3 seconds and 6 seconds. So that's going to be that whole area right there. What's the impulse? All right, let's find it. We're going to go 1/2. This height is 10. The height on the right is 30. So we take the average of those, 10 plus 30, and then take the average, and then we multiply by the width, which is 3. So that looks to me like 40 divided by 2 is 20 times 3 is 60. And what's the unit on this? There are a couple of units that would be okay, but the unit that jumps off the page from our graph is the Newton second. We're multiplying newtons multiplied by seconds when we find the area, so a Newton second is a perfectly good unit there. All right, let's finish this. I've reproduced the graph so we can continue looking at it. What's the change in the object's velocity? The big picture that was a few videos ago said that the impulse is equal to the change in momentum, called the impulse momentum theorem. And the change in momentum, we're assuming the mass doesn't change, but the speed will change. So what we need here, we've got the mass. The mass is 9 kilograms. The amount that the velocity changes, this is one of those problems that's a little bit rare in the sense that we're not asking for the initial velocity or the final velocity. We're just asking for the change. So that's the one that we want right there. Delta V is what we want. Now, to get that, we need to know what the impulse is. Well, the impulse, as we just covered on a graph of force and time, is the area under the curve. Well, the area under the curve from 0 to 6 is this whole area right here. And we said just a second ago that that part of the graph had an area of 60 Newton seconds. We just calculated that just a little bit ago. Now we need to just add in this portion, and that should be easy, isn't it? 3 times 10, so that's 30 Newton seconds. So that means that the total impulse is going to be 90 Newton seconds. So 90 equals 9 times delta V. What's delta V? We can do that in our head. 10 meters per second. That's how much its speed has changed by. We're not told the speed it started at. We're not told the speed it ended at. All we know is that its speed will have changed by 10 meters per second in that amount of time.